All right, I think we start the recording. Okay, Ilmar, the stage is yours. Thank you.
Okay, thank you very much. So, okay, let's start our first, third and last lecture. Let me summarize what we did in last two lectures. So we started with specific quantum mechanics. So the main point here that in order to have a supersymmetry on the level of the ground state, so you should have this E equals 0 as a ground state. So you should have some levels with 0 energy. Okay. So now to check if we have this situation or not, what we do, we compute the Witten index, okay, which shows us if supersymmetry is broken or not. It counts just the states having 0 energy, okay, that actually the difference between bosonic and fermionic ones. So now, how to compute this? So the Witten index, the Witten index is the following thing. So it's just trace minus 1 to the f. This is the Fermat number operator. Okay. Now, how to compute this trace? We used actually the path integral, path integrals, and then and then compute this this Witten index. So I should say that we just started to try to compute, but I just used the formulas for the Gaussian integrals and said that there will be some determinant coming from the Grassmann side and determinant coming from the normal bosonic side. Okay, so now let me try to do some computation just to show you how to get this determinants. Okay, so just for simplicity, I will do this just for bosonic part for the harmonic oscillator. Okay, but then I'll come back to our Hamiltonian, this Hamiltonian, then compute the whole Hamiltonian, this path integral. Okay, so now again, coming back to the harmonic oscillator, so we discussed somewhere the harmonic oscillator. I remember. Okay, I can't find. So we discussed a little bit. Let me write here. Okay, this is our harmonic oscillator. Okay, so as you see, what we do here, we rewrite our exponential in a way that we have sort of Gaussian integral. Okay, then just we know how to compute the Gaussian integral, and then this is just some determinant of our operator there. So now, in order to compute this determinant, we need to find the eigenvalues of this operator. Okay. So now let me just okay. I don't need to copy. So I again. So computation for the harmonic oscillator. So now here in my example, I just compute the partition function. For bosonic sector, there's no difference actually. It will be the same piece in the Witten index. Okay, so the main difference only in the fermionic part. Now, so as I said, the result of the path integral, it's just for the bosonic part. So when I talk about the harmonic oscillator, it's just the usual harmonic oscillator. Of course, you can add some terms and get a supersymmetric one. So I'll write later maybe how to do that. But now it's just the usual harmonic oscillator. So the partition function, it's just trace hit the minus beta h. Okay, so now the result of this, it's just 1 over square root determinant with periodic boundary conditions. So here keep in mind that we have periodic boundary conditions. So this is important. So when we will do this the same for the fermionic part, if we compute the partition, just partition function, then we need to take anti-periodic boundary conditions. Okay, periodic boundary conditions. So, but when we compute the Witten index, then we only have periodic boundary conditions. So periodic boundary conditions here. And then we need, what we need to compute? We need to compute this one. So the term of this operator. So just what's ddt as a matrix? So how to find its eigenvectors? It's not so hard because you know that for ddt, if I write as if I take so here I should be careful which letter to use. So let me use for this situation just lambda. So the eigenvalues of ddt, let's call it lambda n. Okay, eigenvector lambda n, and so this is a function of t. Okay, now lambda n, it's just what is that? So it's just e to the so it's of course it's exponential, yes, because you take the derivative, so you get the same lambda. So that means that's some exponential. So it's just 2 pi I beta over beta nt. So this is easy to understand why it's beta. So we have again this periodic boundary conditions. So you get the same. Now, if you plug this lambda n here, what you get 2 pi I over beta. So what's that? 2 pi over beta times n, yes, and then again lambda n. So this is our vector. Now, in order to compute the determinant of this operator, what we need to do, we need to take the product of eigenvalues, yes. So now, what's the determinant? So let's see. What's the determinant now? Determinant of minus d squared dt squared, again is periodic boundary conditions. Now this is some product over product where k starting from. So let me write first. So this is again 2 pi I beta n. This is the eigenvalue. Okay, this is the eigenvalue of the ddt. So here, since we have d squared dt squared, then what we have here, we have square of this. So it's minus here and square of this. Okay, so and then just omega square, it's omega square. So this is the product. So since it's n, I should write k maybe. So k here, and k runs from minus infinity. So because of this for all n's or for all k's till plus infinity. Okay, so since it's such a linear operator, but it's not a really matrix. It's just derivative. Okay, so it's infinite dimensional matrix if you want. Now you need to compute this. Okay, so actually this is not so hard to compute, but you will see that easily that so what you need to do, you need to take out this piece and somehow rewrite this product as a so if you Taylor expand just sine function, you can easily see that it's sine or cosine, okay, easily. But then maybe I can show you just a few steps. So just few steps what you can do here. And so let me write this in this way. So if you take the square, it's I square and minus gives just plus, and then you have 4p square over beta square k square plus omega square. Okay, so this is the result. Now if you take k square, so since you see k runs from minus infinity to infinity, but we have just k square, that means that this is just square of, so you can say that it's k runs from 1 to infinity, and then square of this 2p square beta square k square. So because k square is always positive, okay, it's the same terms, and then square of this. But what we need to check only when k equals to 0. When k equals to 0, we have only omega square and then omega square. Okay. Now this piece you can write via sine function. Okay, just sine easily. But you see, since k runs from 1 to infinity, you have here some divergence. Okay, and in order to deal with this divergence, what you need to do zeta regularization. Okay, that's important. It's almost regularization. Okay, the correct way. So you need to regularize. Okay, and you need to use zeta regularization here. Okay. So this is always the same story. Whenever you deal with this path integrals, you always get some infinity, some divergence, and then you need to regularize. So maybe I'll come back to this point later about the zeta regularization, but right now I don't want to talk because I don't know if I can explain everything in time or not. So okay, this is how to compute these determinants. Okay. Now coming back to our specific quantum mechanics. Now what I want to do, I want to show you how to compute Witten's for some sort of most general Hamiltonian. Okay, it's not the general one. Of course, you see I have just one dimension, I have just one Grassmann operator, many things. So in this situation, it's not really of course you can have many supersymmetry charges. Here it's not the case. You can consider 2 dimensions, 3 dimensional, 4 dimensional case of 5, 6. So but at least in 1 dimension, it's sort of a bit general, because you see I have just prepotential W in general form. In case of the harmonic oscillator, just take W as a x square, and then if you take the derivative, it gives here just you see you need to take just one derivative. This will give x squared at the end of the day. So this is, you see, it looks like harmonic oscillator, this part, and this gives just 1. Okay, not x squared, maybe x squared. So you take W as a x squared over 2 factorial. Okay, then it gives 1 here, and here you get just x and then x squared again. So if you plug W equals to x squared over 2 factorial, what you get the supersymmetric symmetric harmonic oscillator. So okay, this is square plus 1/2 x squared plus 1/2. So this is also great. Okay, this is what you get. This is supersymmetric Susy harmonic oscillator. Since I'll show the computation for the Witten's for general W, as a homework, what you can do, you can try to do this just for supersymmetric harmonic oscillator. And my suggestion, even to see that the energy spectrum in this theory really has, so that there is a ground state, is the energy equals to 0, just compute just solve the Schrödinger equation or whatever. I mean, you can use even perturbation theory if you cannot solve the Schrödinger equation, and just show that you really get E equals 0. So just let me mention that if you do all computation for this part, what you get E to h omega 1/2. This is the ground state. But if you compute another piece, so then you'll get exactly this minus sign this. So okay, and they will cancel each other. Okay, now this you can check yourself for harmonic oscillator. So this is sort of homework. You can, my suggestion, just even use perturbation theory and see that each term in perturbation theory cancel each other. So each term coming from bosonic sector and from harmonic sector, they always come with different signs and they cancel each other. Okay, at the end you get just E equals to 0. So now, how to compute the Witten index for this Hamiltonian? Okay, for the general one. So again, I can't do all the computations. I'll just show you very roughly how to do that. So again, if you are familiar with the path integral, so what we really need to do, we need to write so this so the Witten index is the following thing. So it's -1 to the f. Now I plug just this minus beta h. So this h, exactly this h. Okay. Now this is path integral with periodic boundary conditions. Okay, periodic boundary conditions. This is for both, for bosonic and for fermionic sector. Okay, boundary conditions. Again, if you want to compute just partition function for this Hamiltonian, then for Grassmann ones, you need to take antiperiodic boundary conditions. Okay. Now this you have dx, d psi, d psi bar. Let me write. Sorry, not d psi bar. Actually, what I used. Okay, I used psi. Yes, yeah. I already confused what I was using. I always use psi. So somehow I remembered that I was using phi, but that's not okay. Phi psi. Okay, this is just Grassmann. So if I remember correctly, I was using phi, but still doesn't matter. D psi bar, d psi. Okay, and then you need to compute such a. So this is yeah. When I write here, so as it's without I, this means this is Euclidean action. Okay, and this of course depends this action on x psi bar and psi. Okay, now but this is again it's important. So we have our Hamiltonian, but this action this is classical. So in what I mean classical, there's no operator here. Classical action. Now, okay. So what we want to do, we want to compute this this path integral. Okay. So if you are familiar with path integrals, so the leading contribution to this integral comes from the critical points. Okay, so so how to so what I mean by critical points, so in our Hamiltonian, so which so I don't want to write the Hamiltonian again, but so we have prepotential V, and the critical point it's such a point, so let me call it x critical. Okay, so the derivative of our potential equals to 0. Okay, so this is the maximal contribution. Okay, so now what we can do, we can expand or consider quantum fluctuations. Okay, about around this critical point. So this is the standard way how to deal with all this stuff. So what we do, we rewrite our action. So the action you are familiar maybe from classical mechanics. So what's the action actually? So in terms of the Hamiltonian, so it's just so if you have Hamiltonian, so from classical mechanics, you know that the action is just the integral, and here you have P dq. This is the momentum, and this is the, so maybe dx, right? P dx, and then minus Hamiltonian dt. Okay, so this is the action. So when you write the everything in terms of Grassmann numbers here, instead of this pdx, or so this you can write also px dot dt. Okay, instead of this you just write phi bar, so phi dot. Okay, so for the Grassmann ones. Okay, now what we want to do, we want to expand our action, okay, around this critical point. So if you expand, so this is a bit it's not complicated, but we need to do some computation now. So let me let me just write some pieces of this expansion. So this is our Hamiltonian. Okay, so again we have some critical points. Okay, so here it's written as a quantum mechanical Hamiltonian. So it's so everything's operators here, but just forget about the operators. Just think about everything as a usual in classical mechanical sense. Okay, so now it's nothing here operator anymore. Okay, maybe I should take this. Okay, so there's no operator anymore. Now we have critical point, and then we expand around critical point. So okay, it's critical point plus some what we can do, delta x. Okay, so this we expand and just keep our Grassmann variables phi and phi bar and phi. Okay, or psi bar, doesn't matter. So since it's written here psi, let me write just psi. Okay, now now if we expand, if you remember in harmonic oscillator, what you really get for the classical piece, it's just x d square dt square, again x, and plus some piece coming from the so this is some piece coming from the so here what we have, omega square x square. Yes, so this omega square in our case, it's just derivative of the prepotential. But okay, let me, this part I can show. So this is what comes from here. Okay, and another piece we should compute ourselves. So then also there's a part, so this is coming from the action. Okay, this is for action integral. Okay, now there's also similar part coming from Grassmann variables. So it's just psi bar psi dot. Okay, now and now there's a part coming from the prepotential. So now let me how to do that. So actually it's quite a lot of computation, so I don't want really to do all the stuff. So what you really need to do, so you need to plug here everywhere instead of x, but x critical plus delta x, and then Taylor expand everything. Okay, that's the whole point. So what one needs to do. So also the same stuff here. So if you will do that, maybe I can write just the result. I don't know. I'll come to this point later when I'll show you that the Witten index doesn't depend on some deformations of the parameters of the theory. So there I can do all this computation. But here, just let me tell you that you need to expand all this stuff, and then what you'll get here, you'll get something like this, like plus here the derivative of the prepotential. So it's derivative of the prepotential. Second derivative, yes, the second derivative of prepotential, and then x times x, something like that. Okay, and also for the Grassmann variable. So again, I will do more complicated computation. So there maybe I can show you. So I don't want to expand this now. Taylor expansion. So just again, Taylor expand and keep these terms. Okay, x squared terms, all the Gaussian ones. Okay. Now, if you do all this stuff, here you can easily see. So it's with minus sign. So here you can easily see that what we have here in Gaussian integral, we have the determinant. Okay. Determinant, square root of the determinant, and here we have minus d square dt square. And then plus d square double dx square, but this is in critical points. Okay, x critical. And of course, if you have many critical points, then you need to sum over critical points. Okay, so and this at x critical. Okay. So this is, I think this is wrong. I'm pretty sure that it should be square. Okay, let me write here square if you take the expand. So this is because you see, if you take the derivative, it gives sort of omega, and then if you take the square, then you get omega square. Now, what comes from the Grassmann side, it's just determinant. Now, in Grassmann side, again, you see this term, it can be like psi bar dt psi. Okay, so in Grassmann case, you have just dt here. Okay, and then plus again just second derivative of prepotential, again at critical point. So this is the all stuff what you need to do. So then, if you know exactly what's the prepotential, so you need to plug your prepotential here and compute this determinant. Okay. So now, but actually, one can do this even for the general prepotential. But again, there you need to do some regularization process. So let me roughly show how to compute this again determinants. Now the first determinant, it's again dt plus d square w dx square at x equals to x critical. So again, this is some number, so or something. So it's not the derivative or something like that. So it's just the eigenvector for this. It's just some vector. Okay, so you just multiply the vector with number or with x or something like that. So for this, we know what's the eigenvector. Okay, so we call that lambda n. Okay, now what happens that this lambda, if it acts on so if we write the eigenvector for this operator, so lambda n, that's just from the first part. So if you remember, it was like just 2 pi I over beta, okay, times n. So it's 2 pi I over beta times n, okay, and plus this second derivative. So okay, just let me write this W prime prime. Okay, so but at critical point. So this times lambda n. Okay. This is eigenvalues of determinant dt plus W prime prime. The another one we already know, so I don't want to write. So if you write that, what's the Witten index now? -1 to the f and e to the minus beta h. Okay. So again, so what we get from here, it's a product of 2 pi I over beta n plus double prime prime. So n running from -infinity to +infinity, and another one was from -infinity to +infinity. Square of this is minus sign 2 pi I beta n square plus what was here, double prime prime square. So now what we need to do, we need to compute these infinite products. Okay, so again, you can rewrite this as a square of the, so at least here in the denominator, what you can do, it starts from minus to plus infinity, but you have only n square. You can write this as a square. So here we have actual square root. Yes, square root. I forgot. So since you have square root, but you have square, this comes out. So if you compute all this stuff, it's not so hard. Then what you get at the end of the day, it's just something like this. So since we have square root here, it's just modulus of double prime prime, and here double prime prime, but double all the w's at critical point. Okay, so and then of course I forgot there's a sum over critical points. Okay, and here you of course have sum over critical points. Okay, so this is the result for the Witten index for our Hamiltonian. And just choosing different prepotentials and plugging here, you can get the Witten index. Okay, the result of the Witten index. You can see here it's not zero actually for the case if you choose just W as a x square. Okay. If it's just harmonic oscillator, then you get just 1. So for the harmonic oscillator, so Witten index. So the harmonic oscillator, what I mean is, I mean that W actually equals to W equals to x square over 2 factorial. Okay, so it's x like this. So for the harmonic oscillator, you can see that the index actually equals to 1. So from this computation, okay. Now let me rewrite everything in a different way now. So as I said, the Witten index is a topological invariant of the theory. What it means if you deform the parameters of the theory, the Witten index will not see that, and you'll get the same result. So, but before starting to do all these computations, just again, this will be some sketch how to show that. Let me ask if there are any questions. Okay, if not, then then let's do this, at least this part, in the case where we have deformed potential. Okay. Now, again, coming back to this point, so that we want to compute trace of -1 to the f and e to the minus beta h. Okay. So we want to compute this this Witten index, and the what I'm saying that it's sort of topological invariant. So in my case, I just want to show that it doesn't depend on the deformation of the parameters of the theory, but at the same time, of course, if you consider your theory on a manifold and compute the index, you can show that it's related to the Euler characteristic of the manifold, but I'm not going to talk about that story. I'm just what I want to do. I want to do some continuous deformations of the parameters of the theory. Okay, so what I mean by deformations here. So again, we have this Hamiltonian. Just for this Hamiltonian, okay. Let's start with this Hamiltonian. And now what we want to do, we want to deform our prepotential. What I mean, we want to deform, actually, let's say that if you have, so it's sort of doing, you know, deformation. What I mean by I want to deform, I want to deform my coupling constant in some sense. So what it means here. So if you have some prepotential, then let's deform the prepotential. So that means that let's, instead of W, write some constant G times W. Okay, so you can do this deformation. Okay. Now, in case of the harmonic oscillator, what will happen, that here, if you have W equals to x squared over 2 factorial, now instead of W x squared over 2 factorial, you have now G times x squared over 2 factorial, and then what you get here is 1/2 and G times x squared. Okay, so this is sort of now a new coupling here, and also the same here. Okay, now what we mean that with the index is invariant and the deformations, that means that if you compute the index now for this theory where you have deformed potential trace of, so the Witten index will not see this G. Okay, so it doesn't depend on this G. So okay, so now now how to do this computation. So actually I can do much. So just deform this and then also take G to infinity. This will be some deformation of the prepotential. Yes. So but still how to show that it doesn't see this deformation. So what I will do, I will compute and send G to infinity. Okay. So how to do these computations? So again, use the path integral. So we first compute the actually I forgot when I used expansion around. So but there is also piece coming. So I forgot to tell you. Now I remember. So so when you compute the partition, right? So when you compute the Witten index, when you expand and compute the index around critical point, of course you get this piece, but then times, of course, you have everywhere the piece coming from the critical point. Okay, so that piece you can easily compute yourself. That will be in our case just one. So I forgot to tell you. So now again, what I do, the written index, so it's written here, good. So this is some path integral with periodic boundary conditions, okay? And now what I'll do, I'll compute this index for the case where I have S, but in S I have not just W, but G times W, okay? So again, just expand this action, okay, around critical points. So then, of course, we need to compute the action at the critical point. This is easy computation. Just you can do this yourself. So at critical point, let me write like this. So at critical point, this summation. So what you'll get. So let's say that I compute at critical point. So this is index. So it's sum over x critical e to the minus s is x critical, okay, and this you can compute yourself, and this gives just sum over critical x critical, and this actually will give something like 1 or some constants, probably 1. Okay, this is not so hard, because you see, to compute at critical points, you don't need Grassmann variables, because you have just this, your prepotential depends only on x, so you just plug x critical in your prepotential and forget about the Grassmann ones, and then it's easy. So okay. It's because your classical trajectory doesn't see your Grassmann. Sorry. Now, this is easy computation you can do yourself, but then what you need to do, you need to expand around this critical point again and compute the action. So if you will do such a computation, so let me see, I have 30 minutes, yes, 45 minutes. Okay, so let me try to show you then. Now, now what we want to do, we want to, actually this is G square. So what we want to do, we want to plug G times W in our Hamiltonian, then expand around the critical point and see what we will get. So expansion again, it's x critical plus delta x, and with Grassmanns we keep just Grassmann ones, okay, psi bar and psi. So we expand around x critical, and then the action again equals to this integral. Okay, actually our integral from 0 to beta. Okay, now what we have here, we have again just this. So since I expand around this critical one, so here it's minus and delta x d square dt square, and here I have again delta x. Okay, so this is from Bosonic part. Then I have again psi bar psi times psi dot. Okay, so this I can rewrite as a psi bar ddt psi. Now then what I have this W term. Okay, so this I need to expand. So let me expand this. So here what I have, so I plug this now in my W, so it's W bar, insert double prime times G, and this is square. So this is this term. So it's 1/2. So now let me expand this. So it's 1/2 G square, okay. And then since W depends on X, this X critical plus delta X and square, then it's 1/2 G square. Now, if I expand this, this is just W prime at X critical plus W2 prime at X critical delta X and so on. So I don't need all other terms, okay, because then it will be delta X square, and but square of delta X square will give delta X to the fourth, and this is not Gaussian anymore. Okay, you see, I need to plug this term here. So let me write 1/2 G square W prime at X critical W2 prime delta X and so on square. And the same I should do with W2 prime, okay? But there it's easy because you see what I have here, I have G times W2 prime, okay? And with 1/2, okay, in front. So here I need to expand, but it's easy. So if you expand, it's W2 prime at X critical plus W, so it's plus W2 prime at X critical delta X, but this term and plus other terms, but even this term I don't need, because then I'll get delta X times psi bar psi, so it's mixed term, okay? This is also not Gaussian, so I don't need this term, so I need to keep just this term. So if, and let me just add here again, this, the last term, it's just 1/2 G and W2 prime psi bar psi, okay? This is, so this is sorry, I use bar as for psi. Okay, so this you can write just as a psi bar psi. So before, if you remember, we used for so if you remember in Hamiltonian, I was using just bars instead of dega. I forgot now. It was here, so I used phi bar and phi for that. Okay. But so since I'm writing just classical action, not the quantum Hamiltonian, okay, so we just have psi bar psi here, or in our previous notation it's just phi bar phi. Now this is our action, okay. So now if you you can easily see that what we'll get from here. So we have G square in front of, you see, W2 2 prime, and G in front of W2 prime here, okay, where we have Grassmann numbers. So when you compute the Witten index, okay, so what you get actually, you get here the sum of critical points, and here it's determinant ddt and plus W2 prime. So this W2 prime comes from W2 prime psi bar psi, but in front of that we have now G, so it's, you have G here, okay, and then determinant square root of determinant here, so it's minus d squared dt square, okay. And now what we had before was just double prime square, so this term comes from this square, okay, from this one, or from this one. So now in front of that term we have G square, so G square, so G square, and this W2 prime square. So now if you compute everything again, okay, just using this eigenvalues of this of these operators, what you get at the end, you will get that there's a sum or critical, and here what you have just G times W, G times W2 prime, and here G times W2 prime, and then just you can take out this G because it doesn't matter. Of course, you can say that, but taking out it will change the sign. If it's so, we actually start with positive G, but even in the case that it will change the sign, that gives nothing, because it's not important if you get minus or plus sign for the Witten index. What's important if it's equals to 0 or not. So you can say, you can define your index as a number of bosons minus number of fermions on the ground state, or vice versa, number of fermions minus number of bosons. So what we want to understand that if it's equal to 0 or not, but the plus or minus sign is not important. So you can simplify, and then you get this just x critical W2 prime over 1. So this is the result showing that your index is independent of G, and that means that the Witten index, so sort of topological, the Witten index is topological invariant of the theorem. So this is about the topological invariance of the Witten index. Okay, so maybe I can stop here about all this stuff, and if you have questions, please ask your questions. You can try to give answer. If not, then I can continue to talk about the applications. So questions, please, if you have. Okay, so if there's no question, so my suggestion for you to do all this computation for the supersymmetric harmonic oscillator, okay, it's not hard. So if you will do all these computations, just doesn't matter how you get really the bosonic and fermionic parts, just compute it, and then what you'll get just so let me tell you the important point here, maybe. So let's say that you want to compute the index for the system. So for the harmonic oscillator, in order to have this supersymmetry, what you really need to get. So let's add the Hamiltonian. Okay, so the harmonic oscillator. It's very important that you have the same omegas in the specific harmonic oscillator. So if you start with your Hamiltonian, so okay, so and say that you want to write your Hamiltonian in terms of the creation and annihilation operators. Okay, so if you write the Hamiltonian in terms of creation and annihilation operators, okay, it's just a dagger A plus 1/2. Okay, so this is the for bosonic part, and let's say that this has omega bosonic, and then you want to add some Grassmann story here in order to get fermionic part. So then you can add the omega fermionic here. Okay, and then what you have here, so let's say that you have psi dagger psi minus 1/2. Okay, so similar story. Okay, and then if you start with this sort of supersymmetric harmonic oscillator you do, then you will see that for such harmonic oscillator, if you compute the Witten index, okay, e to minus beta h, okay, if you will compute this trace, of course, this trace, this index will depend on beta. Okay, so and in for the for such harmonic oscillator, of course, you will not get zero ground state. Okay, so because you have different omegas. So if you compute the energy level for this, so what you will get so 1/2 h omega b minus 1/2 h omega f. Okay, this is the result of which you will get. So in order to cancel these terms, what you need that omega b equals to omega f. So the frequencies should be the same. So in order to get supersymmetric harmonic oscillator, okay. So if you compute this trace, you can easily see that only when WB equals to WF, omega B equals to omega F, you will get Witten index independent of beta. Okay, so in order to have supersymmetric harmonic oscillator, you need to choose the same frequencies for fermions and for bosons. Okay, then just compute the trace of -1 to f times e to minus beta h. So it's again using this you can do even without using path integrals. For at least for bosonic case, it's easy because you know the exact result. Okay, so then just compute it and you will get just 1. Okay, so it's just 1 for harmonic oscillator. Okay, so that means that you have some states with energy equals to 0. Okay, with 0 energy for supersymmetric harmonic oscillator. Now, this is sort of some homework for you. So I was very fast doing all this computation. So actually, then what you can check also, you can change your frequencies and see that if even the result doesn't depend on the frequencies. So okay, so that's sort of changing the parameters of the theory, the formation of the parameters. And this keeps your preserves the Witten index. Okay, so okay, now let me tell you a bit about the generalization of the Witten index. So now all this story was about the supersymmetric quantum mechanics. It's again very interesting object. So it has so an analog. So actually, probably Witten used this analog from the mathematics. So it's related to the Atiyah-Zinger index. So there's the index theorem. This index, so it has many features. So related to mathematics, related to physics. So you can find this in many books. Now, there's another story how to generalize this index to the supersymmetric field theory. So this was done actually just as an index by Witten. So it was in the 90s and later. So also I think in the beginning of 2000. So he computed this index for supersymmetric gauge theories, and there it's related to the rank of the gauge group. Now, but still one can get more information from the index if we can use some other symmetries of the theory when we define the index. So this is a so-called generalization of the Witten index. So now again, for the field theories, we have what we have the supersymmetry algebra. So let's say that we have field theory generalization. So for the field theories, what we have supersymmetric algebra. So let's say we have Q Dagger, okay. And what we know that this is a symmetry, so that means that Hamiltonian with Q and Q Dagger gives the commutator with Q and Q Dagger gives 0. Okay. Now that means that Q and Q Dagger generates the symmetry. Now let's say that we have some other symmetries, okay, which commutes with the supersymmetry. For instance, in supersymmetric gauge theories, what you can take as such symmetry, you can take some global symmetries. For instance, flavor symmetry, it commutes, of course, with the supersymmetry. Okay, so let's say that you have some flavor symmetries. So just for instance, flavor symmetries. Okay. And they also symmetries, and they also commute with Q. Okay, so let's say it's F. Let's call this your symmetry. So it has nothing to do with F of the Fermat number operator. Let me write this like this F. Okay, so this is other symmetries, for instance, flavor symmetries, and they also commute with Q and Q Dagger. Okay. So what it gives if we have some commuting operators here. What we can do in this situation? So then we can generalize our Witten index, generalized index, in the following way. So now we have trace minus 1 to the F. Okay, so this number operator. So here you have e to the minus beta h. Okay, this is in quantum mechanics. But now, of course, in case of the supersymmetric gauge theories, it's not just h, because the Q and Q Dagger could give something else. So you can call it H, of course, but what I mean that it's some combination of some generators like angular momentum, the usual energy, and for instance R symmetry and so on. So what's R symmetry? It just rotates your supercharge. So let me write instead of H just Q and Q Dagger. Okay. Yeah, so anticommutator Q and Q Dagger. Okay, and now what you can do if you have some other symmetries which commutes with supersymmetric charge. So this is important. So if your symmetry commutes with supersymmetry, then you can add this supersymmetric this charge here. So it's just not plus times. So what you can do, you can write just e to the some let me write it's small f times f. So this is just chemical potential. Okay, it's just chemical potential. So now what's the meaning of this generalized index? Why it's again it's index? So because you see it doesn't depend on beta. How to check that? Again, very roughly, so let's call E generalized. Okay, so how to check that it doesn't depend on beta? Just take the derivative. Okay, dE generalized d beta, and you can easily show that it equals to 0. Okay, so why it's like that? Because you will get Q Dagger in front of the exponential, but they commute with flavor symmetries. There is no problem, and then you can easily show that it's really index again. Okay. Now, of course, this is not number anymore. So this index, of course, now depends on on chemical potential. Okay, so again, if you just forget about chemical potential, it's again the index. But in case of chemical potential, F, if you have F, then it of course depends on F. Again, it doesn't depend on beta, but it depends on F. And if you have many symmetries, so for instance flavor symmetries, okay, then you have many Fs. Okay, so for instance, if you have as a flavor symmetry some SUN flavor group, then you have NFN, so n times of Fs. Okay, so you have n chemical potentials. Okay, now this index was introduced, the generalization, I think at the end of the 80s or in the beginning of 90s, by Sen, but it was somehow the papers of Sen, everyone forgot about his papers. Somehow no one realized that it's some interesting object, and then only in 2005, two groups, one Rummelsberger, I say Rummelsberger. Okay, I sometimes I forget names. I'm sorry if I wrote the wrong name. So another one, Kinney, at the same year, Kinney, Minwalla. So I'm not sure about all the names. I'm sorry. So Kinney, Minwalla, Maldacena, and someone else. I don't remember. Oh, there should be one more name. So they introduced this index, okay, and this now the name of the, so it has name so-called super conformal index at that time. Why it was super conformal? Because so they considered actually super conformal theory, where you have supersymmetry and also conformal theory, symmetry conformal. So the Kinney, Minwalla, and Maldacena, they consider n equals 4. Spirian Mills, that has actually it's conformal theory. Rummelsberger considered n equals 1 theory, but on special manifold S3 times S1. So that's also conformal theory. Here, and here it's n equals 1. So this is some super conformal index. Okay, so this is very interesting object. Why it's interesting from many points of view? Because you can get many information about the theory. So since it's super, so you see, since you add, so here, so the way how you compute this index, you just plug one supercharge here, so it's related to the BPS counting. So you count BPS operators here. So not all of them, of course, but depending on the theory, I mean, how many supercharges you have in your theory. So, but coming back to the point, how to compute this index now using the sort of path integral. So what we can do here. So again, if you remember, we were using periodic boundary conditions. So here the index is again something like partition function, but it's a bit different here. What you need to do, you need to be careful about the boundary conditions in your path integral, and here it's or function integral, doesn't matter. So here you need to use the so-called twisted boundary conditions. Okay, so that means that when you, so maybe I can write here somewhere. So what it means, before we had just periodic boundary conditions. So for bosons and for fermions, means that just x t plus beta was just x of t. So and this we used in order to compute our determinants. Okay, and these periodic boundary conditions we had also for for our psi's. Okay, so t plus beta, it was just psi of t. Okay, now now one needs to be careful because we have such a piece here. Now you see this e to the f phi. So now one needs to use twisted boundary conditions, both for fermions and for bosons conditions. So that means that when you have x, for instance, t plus beta, now you get not just x of t, but times this piece, so but bosonic one. Okay, so it's just e to the f x of t. So it's twisted by this exponential. Okay. So then just use the previous. Okay, of course it's not so easy to compute such an index in specific. So in case of supersymmetry quantum mechanics, of course it's easy to compute. So again, it's the similar computation. So you can do this generalization also in supersymmetry quantum mechanics. So it was done. So for many theories, people computed, and there are many results. So this you can do, of course. But in case of the quantum field theory, it's not so easy. So it's not so easy, and the first result using like exactly like what we used in our example, like path integrals. The first result I think was in 2006, I think. So it was the result, so not for the index, but by Peston. He used the localization technique, and later people used this localization technique just to compute. So he computed partition function for n equals 4 super-Young's theory on S4, so on a sphere, and then later it was used his technique by many authors just to compute the super-conformal index. Super-conformal index. So the main tool here to compute is so-called supersymmetric. I'm not going to talk about that, but just localization. So first by Peston. So this is now main technique in supersymmetric gauge theories. So in order to compute the index, you just compute the sort of partition function, but with twisted boundary conditions. So actually the written index, it's index, the generalized one, of course. It's just the index in 4 dimensions. It's on S3 times S1. Just consider your theory on S3 times S1 with twist boundary conditions. In 3 dimensions on S2 times S1. Okay, this if you consider your theory with twist boundary conditions, so compute the index, then you will get some interesting results. So it's again not number. It depends on in our case. Actually, I just used flavor symmetry. It depends on flavor symmetries. Of course, it doesn't mean that it only depends on flavor symmetries. Again, you can plug any symmetry. It's not only global symmetry. If you have some symmetry which commutes with your supercharge, just plug it as an exponential, just using some chemical potential. Then, of course, your index depends on this chemical potential. Okay, so and since this is the symmetry of your theory, so this f comes from the theory, of course, then generalized index again knows a lot about your theory. So at least it knows all symmetries of your theory. If you plug all symmetries which commutes with supercharge, then it knows many things about your theory. So you see that even by construction, it's in principle possible to tell something about the theories even without Lagrangian description. Okay, so just if you know the symmetries of the theory, you just plug everything here, try to compute somehow, and then you can tell something about the theory, even if has no Lagrangian description. Okay, this is some modern stuff about the index. Okay, so there are a lot of results now. It's so it's computed this generalized index for many theories in quantum mechanics. So there are a lot of results. I mean, for generalized one, of course. Yeah, maybe I can stop here just on this. And if there are some questions, I can answer the questions. So, but if not, then maybe I can make some more comments about the last things which I explained now. Okay, so questions if you have. Actually, I don't see any, like the chat and other things. I hope there are not any question or like in the chat. I hope you have some questions to ask, but not at least in chat. Is there any question?
İlmar Hocam, bir şey sormak istiyorum. Sizin merak ettiğim bir konu var. Bu süpersimetrik teoride standart modele gelen katkı tam olarak nedir hocam? Mesela SU3, SU2 ve E2, E1 simetri gruplarına ek olarak nasıl bir katkı geliyor?
Okay. Okay. Let me just then. Okay. So the question about the how to see what's the impact of the supersymmetry in standard model is. So, but the point that actually there's no supersymmetry. So there's no such a symmetry in standard model. There is a generalization of the or how you want it. You can call it generalization or standard model with supersymmetry. So you can add such a symmetry to the standard model actually, but then it's not really the usual standard model which you know. So in standard model, it's easy to understand at least why there's no supersymmetry. So even you can check that there's no supercharge, blah blah blah. But still, even on the level of the particles, you see that you have some fermion, for instance, electron with some mass. For instance, electron mass, it's 1 MeV. So, but there's no such a boson. Okay, so there should be a supersymmetric partner for each particle. Okay, because again, this is symmetry between bosons and fermions. Okay, so that means that in your theory, what you can do, you can change all fermions to the bosons and bosons to the fermions very roughly. Okay, and then you still have the same theory. Okay, so for that you need some supersymmetric partner for all particles. And okay, this is another story that they should the supersymmetric particles. So the pairs, they should have the same mass, but so at least you have a electron as a fermion, and there's no partner for the electron supersymmetric partner with the same mass. Okay, so this, if there is such a particle, then it's easy to in some sense easy to detect that particle, but we never detect it. So there's no supersymmetry in nature in some sense. Okay, so what we believe that there is a supersymmetry on a high level, high level, I mean in the energy. So if you and why we need this supersymmetry, there are many reasons. Okay, so from my point of view, I just find this very beautiful theory. And it's not only in standard model. Maybe we will find okay, the supersymmetry is not a theory. You see, it's just some symmetry. So you can find this in some special models, not only in standard model. Okay, maybe in condensed matter, in some. In other, it's from my point of view, it has some nice mathematics and it's very beautiful symmetry and it's very natural. But on the other hand, so we have many problems with standard model. Okay, the unification problem, with hierarchy problem, dark matter, dark energy problem, and many things. So, and some people think that it could be some solution for these problems. So now, there is no. Of course, again, in standard model supersymmetry, when you add this supersymmetry, there are many minimal theories, minimal supersymmetric extensions of the standard model. There, of course, you add this as a new symmetry. Of course, it changes your Poincare algebra. Of course, now then, if this depends, of course, how many supersymmetry you want to add. So this minimal models has just the minimal supersymmetry, number of supersymmetry. So you add and then you get some different algebra. Okay, that's the point. But in usual standard model there is no supersymmetry, of course. So again, you even don't need to check if there's some supercharge or not in your theory. Okay, so there's no, of course, but still you don't even need to do that, because again, for supersymmetric theories you need supersymmetric partner whenever you have. So even here you see on the level of supersymmetric quantum mechanics, if you have bosonic sector, then you need to have fermionic sector. Okay, it's not like you have just one sector and then there's no point of the supercharge. So supercharge actually acts on your bosonic sector and gives fermionic, or vice versa. So hope this was the answer which you want from me. Okay, that is fine.
Teşekkürler İlmar Hocam. Sağ olun.
Okay, so any other question? Just let me tell you, maybe one can ask, but this is quite a complicated question, maybe just to explain in a few minutes. So let's say that if you can compute with an index, what we can tell about the standard model. Well, let's say that we expanded supersymmetric the standard model, find the, let's say, correct supersymmetric standard model in some sense, but then of course in the nature we see just standard model. Okay, that means the supersymmetry is broken. Doesn't matter how, but it's broken. And when you break the supersymmetry, of course we cannot talk about the index, of course, yes, because the index, you see, it's exactly about the supersymmetry, and if it's broken, there's no index. Okay, so if you can put it, it will give like zero index supersymmetric gauge theories, for instance. Now, what we can learn from these objects, okay, the main point probably of these objects, of these topological objects, we can, studying these topological objects, we can somehow maybe better understand such objects maybe in condensed matter. This is one point. So it's interesting, first of all, from mathematical point of view. But on the other hand, when you do this generalization, for instance, this generalized index, it sees also all anomalies of the supersymmetric gauge theory. So you can compute anomaly coefficients just if you know the index. Okay. So now the question, but the anomalies of the supersymmetry theory and the anomalous of the broken theory, it's not the same, of course, because you see you have just one sector in the broken system. But still, maybe later, I don't know. Right now, it's too early to talk about that. But studying these objects and after breaking the symmetry, supersymmetry, actually, still maybe we can say something interesting about the broken theories. Okay, just knowing these objects. Again, some features which has these computations, at least we can translate these features to the broken theories, I mean, to the theories without supersymmetry. Okay, so but right now, of course, it's hard to say that that why we study this if there's no supersymmetry. Again, from the particle physics point of view, it's not maybe so interesting objects in some sense.
Ilmar Hocam, thank you so much for this beautiful talk and your comments on the general utility of the supersymmetry. And let me stop the recording.
Okay, thank you very much for the inviting me and for the listening my lectures. Thanks.